Hello and welcome back to Calculus 1. The last section in chapter 3 on related rates. So we are going to apply the knowledge on implicit differentiation and chain rule to one of my favorite sections. These are the word problems, and we get to take a look at many different situations. So let's talk about related rates. Well, first off, let's deconstruct the title. Related rates. We know that our derivative is a rate of change. So we are going to somehow connect multiple derivatives. So related rates means you are going to end up with a formula which has multiple derivatives. Now, these derivatives are usually all in respect to time, because the change in the world around us happens in time. So I'm going to give this example of a melting ice cube. So if we have a perfect cube which has a on sides, we have the volume of that ice cube to be a cubed in inches or centimeters or whatever units you have. So now you have your volume as a cubed, and you can differentiate this formula in time to see the change of volume in time and the change of length of a side in time. Because just think about it. As the ice cube melts, let's say you put it outside on the sun, as it melts, it's becoming smaller. What is becoming smaller? Everything about it is becoming smaller. Each edge, right, the A, each side is getting smaller, the volume is getting smaller, surface area is getting smaller, diagonals are getting smaller. So as the ice cube melts, everything about that ice cube is getting smaller in this particular case. If you are inflating a spherical balloon, like a weather balloon, then everything about that balloon is becoming bigger. The radius of the sphere, right? Or you have, let's say, a soccer ball or something is deflated, and then you put the air in it and it expands. So if you are doing something like that, the radius is getting bigger, the surface area is getting bigger, the volume is getting bigger. So these are connected. So if I take my volume formula for the cube and I differentiate this in time, I will get the rates of change in time, because you have to wait for ice cube to melt to lose volume. You have to wait, right? And that's time. So when I differentiate V in respect to t, I get 1 times dv dt. When I differentiate a cubed, I get 3a squared, and then follow with the chain dA dt. Remember, we learned in our implicit differentiation section that any time when you take the derivative of a variable in respect to a different variable, you have to follow with these chain rules. Every time we took derivative of y in respect to x, we had that term dy dx, right? So now, when we are differentiating in respect to time, well, we're always going to have these dv dt's, dA dt's, the whatever else we get. So now, this formula, we can now drop this one, because we don't need it. And this formula here is related rates. Because you have two rates, as rate number 1, rate number 2, that are related with the rest of this stuff that is in there. So now this dv dt is the rate of change of volume in time, or in respect to time, and dA dt is the rate of change of length of the edge. And we see that they are directly related. So if one gets bigger, the other one must get bigger. If one gets smaller, the other one must get smaller. Because it's always multiplied into a positive number here. In order for you to have a cube, you have to have a positive measurement for the side. When you square it, it's still positive. 3 is positive, so this number is always positive. That means that the sign of this value and the sign of this value is always the same sign. For the loss of volume, we would have a negative. For the gain in volume, we would have a positive. That's what we use negative and positive for from math. So now I can calculate how much volume I am losing when the length of a side is at certain point, and I can measure that. So this is what related rates is. You will have to figure out what kind of geometry you have. Is it a triangle? Is it a cube? Is it a sphere? Is it a circle? And use the formulas. What formulas? Well, it's either the area formula, the volume formula, the Pythagorean theorem formula, the trig formula. Use one of those. And then you differentiate. And then you get your related rates. Then you plug your numbers and you calculate what you need. Let's take an example of, so this was, I said ice cube, right? Let's see the oil spill. Hashtag BP, right? Or pretty much any other. Doesn't matter. So you have oil rig somewhere in the ocean or a sea, and something goes wrong and it spills oil. Oil sticks on a surface and it spreads in all directions unless there is current of some kind. So when the oil spills, it propagates around the oil rig, making the circle of polluted water bigger and bigger and bigger and bigger. In time, the longer you wait, the more cleanup you have to do, because it spreads. And it doesn't spread linearly either, right? It's because the circle on the outside has a bigger area in this ring than this ring, than this ring, right? So the more you wait, the worse it gets. So what is the geometry of this problem? What type of a shape do we need to investigate? circle. So we have a circle. Now, what is that we are concerned with the circle? The area of the circle, because circumference is just the ring on the outside, but all of this is filled with oil. So it's area. Area is the one because the oil is across the entire region. So we say area. Circumference is just the black line on the outer rim. So when the oil spills, you don't get just a rim around, you get everything filled inside. So that's the reason. So we recognize geometry. It's a circle, and then we recognize which formula from circle formulas we get to use. Now, for circle is easy. We only have two. We have a circumference and the area. You have more of them for the ball, right? You have the volume, you have area, you have well, no, that's it. Volume and area for a ball, and volume and circumference, area and circumference for the circle. All right. So area is equal to pi r squared. So area depends on the radius. Radius is the measurement from the center to the edge of the circle. So now we differentiate that in time to learn how one changes as the other value changes. So we have dA dt, which is the change in area of the infected, right, waters, polluted waters in respect to time. On the other side, I have pi 2r dr dt, change in length of radius. So now my related rate formula is dA dt is equal to 2 pi r dr dt, and that's my related rates. So it tells you by how much the area is changing as the radius is, and then you get, and also the change in radius. Now clearly, the more you spill, the faster it changes. The less you spill, the less it changes, and so on. So say that your for this particular problem, say that the rate of change of radius is 30 meters per hour. Rate of change of radius equals 30 meters per hour. And then they say radius is 100 meters. Find rate of change of area. Well, we already have the formula. It's important to realize that anytime when they say a rate, that number goes for one of the two rates. Now you have to be careful which one, right? So rate of change of radius is, here is my rate of change of radius, so it's dr dt. All of this happens in time, clearly. So it's 30 meters per hour. Why did I write units? Well, units are the ones that help you figure out which one it is. What's the unit for area? What's the unit for area in terms of meters? Yes?
Meter squared.
Meter squared. So look, I have area over time. So this has to be meters squared over hour. And this is a radius, which is length. So I have a single meter. That's another way how I know that this is the rate of change of radius. The rate at which you drive is 60 miles per hour. It's a rate, speed, but rate. Rate at which you drive, you're covering 60 miles in 1 hour. So you are driving at that rate. So now you have a rate over here of change of radius in time. So you have 30, and here, single radius, single meter, single time, single hour. Now we are looking for dA dt. That one will be meters squared. Now if you think about units from physics, you have your meters per hour, and then this radius in the formula is another meter. Meter times meter is meters squared, and then a single hour on the bottom is a single hour on the bottom. These formulas must line up dimensionally like this in terms of units. Otherwise, the problem and calculations and everything is going to be wrong. So we start by first figuring out what is the type of information given. As soon as you see the word rate, you immediately know it's one of your derivatives. Then with using units, try to figure out which one. We also say that radius is equal to 100. They are looking for rate of change of area. So when you read the problem and you write out all of these things, plugging it into formula and calculating would be a joke. Because now I know I'm looking for dA dt. On the other side I have 2 pi, r is 100, and this one is 30. Right? So this is 6,000 pi meters squared per hour. So if you are gaining almost 20,000 square meters per hour, you want to make sure that the cleanup crew is there as soon as possible. Right, because pi is 3.14 times 6, so it's not 19 yet, but we can round it off. So these are related rates. You read the word problem, you understand what it's talking about, then figure out geometry, figure out the formula, differentiate. Well, the formula you have at the end is your related rates. Then pick up the numbers that you have to plug in, make sure the units make sense and that you're plugging in the right spot, and then you do the calculation and you're done. So let's take a look at a few examples. Melting the snowball, problem 21. Melting the snowball. A spherical snowball melts at a rate proportional to its surface area. So snowball is melting at the rate proportional to its surface area. Show that the rate of change is of radius is constant. Show that the rate of change of radius is constant. Okay. They are mentioning surface area, and snowball melting means losing volume, right? So now, what do we have here? We have the surface area as 4 pi r squared. If you ask me how I know that, I learned it. It was not communicated to me by anything. I just learned it. I'm just going to call this area instead of surface area. The volume is 4/3 pi r cubed. They want to show that the rate of change of radius in time is constant. That's the goal. Okay, let's see. The derivative in respect to time of our area equation is going to be dA dt is equal to, when I differentiate, I get 8 pi r dr d theta. I mean dr dt. And when I do the same on the volume side, you are going to get that the change of volume in time is 4 pi r squared dr dt. Oh, haha. We have to change this. I have to change this stuff here because of the sentence in this problem. So this is the formula for volume. I'll just put this way, standard formula. We have to modify formula because the problem said that it's proportional to its surface area. When something is proportional, if you say because of the problem statement here. Let me just quickly deal with this thing proportional. When I say that y is proportional to x, I get to write y equal kx. K is the constant of proportionality. If you want to scale something up, you multiply by 2 or multiply by whatever value, but you have to do that across the board. You can't just increase one size and leave the rest, right, the way it was. So when you're talking about proportionality, the K is a direct proportion, and you have the inverse proportion. Like if they say inversely proportional, then it will be K over X for inverse proportion. We'll try to find a problem with that as well. So now, because they're proportional, the volume would be K times 4 pi r squared, because it's proportional to the Wade's laws. So we are not using the actual formula for volume as we should, because the statement says that the rate at which the snowball melts, which means losing volume, so volume formula, is proportional to loss of surface area. So if we differentiate here, we'll have K8 pi r dr dt, dv dt. So when you divide these two, right, you will find that there. Let me see. Okay, let me try something else too. If we go from here and write volume is equal to 4 pi r cubed dr dt, and this is your dv dt, and these two are, and we say that dv dt is K times dA dt, and you can connect. Okay, we can solve it this way too. It's less confusing than introducing 5,000 different formulas. All right, so this is the standard formula for volume. You take the derivative, you get your formula for volume, and this statement here, sentence melting proportional to surface area, that's the sentence that sparks that particular connection between the two worlds. You know that area and volume are not the same. Area is the surface area on which you get to draw, and you can't walk into a 2D area. It's just area on the surface, right? You can walk over it, but you can't walk into it. Now you walk into the volume, but you don't get to draw on the volume. You can draw on the surface. So they're two different, I mean, dimensionally one is 2D, the other one is 3D, and all of that stuff. So now, in order for us to equal them, we have to have something that links those two separate dimensions. Now, in this case, they say it's proportional, so I can just plug in this K. So now, when I get to this, situation here, I get to write, because my dA dt is the same as K, dV dt is the same as K dA dt, I just replace this. So I plug this in here, and this in there, and I work it from there. So what do I have? Instead of a dV dt, I have 4 pi r cubed, I'm doing this red, dr dt is equal to K, dA dt is 8 pi r dr dt. Oh, this is supposed to be a square, guys. It's supposed to be a square. I'm really not happy with this because these guys cancel, this cancels, this cancels, one of the R cancels, and I get that R is equal to 2K. I picked this problem on purpose because it doesn't have calculation, it's just mathematical manipulation. Surface area, 4 pi r squared. The derivative of that, 8 pi r dr d theta, good. Volume, 4/3 pi r cubed. Derivative, when 3 drops from r, cancels the 3, 4 pi r squared dr dt dv dt. The sentence says, a spherical snowball melts at the rate proportional to its surface area. That means that the volume is equal to constant to proportionality times dA dt. Then we plug in dv dt, which is 4 pi r squared dr dt equals to K 8 pi r dr dt. So when everything cancels, I get that R is equal to K. So if R is equal to K, K equals R, then we get that dV dt is equal to R dA dt plug everything in again, subtract equal to 0. Let's see. So 4 pi r squared dr dt is equal to 8 pi r squared dr dt, and that's not good because these are, what the hell is going on? This is supposed to be the simplest problem done in like 2 lines. Why is this so? My head is absolutely not working on this problem. I just don't see. I just need to get dr dt is equal to some kind of constant. That's the answer. I don't see where I get that right now. Because when I plug them in here, they can't, dr dt cancels. I need dr dt to stick around. Okay, if I don't cancel anything, leave everything as is. Move everything to one side. 4 pi r squared dr dt minus 8k pi r dr dt equal to 0. factor out 4 pi r dr dt in parenthesis r minus 2 equal to 0. There we go, finally. Holy nightmare. That's it. From here, we conclude that dr dt is 0, the derivative is 0. No, but that's not constant rate, that's a 0 rate. You know what? Does anyone have any Apple device that you don't want anymore? I just have a urge to break something now. It's like iPhone or iPad or anything. Please. No? Well, you're no help now. Snowball is melting at the rate. Snowball is melting at the rate proportional to its surface area. I'm just gonna. Snowball is melting at the rate proportional to it. There you go. Snowball is melting at a rate proportional to its surface area. Area is given as 4 pi r squared. Show that dr dt is constant. All right. So snowball is melting proportional to the surface area. Surface area is given by this. So dv dt is equal to k 4 pi r squared. Now, volume is 4/3 pi r cubed. dv dt is 4 pi r squared dr dt. When we differentiate, 3 kills 3, 4 pi r squared dr dt. There we go. So now 4 pi plug in. So this one goes there. 4 pi r squared dr dt is equal to k 4 pi r squared. 4 pi dies with 4 pi, r squared dies with r, and there it is, dr dt equals k. Holy nightmare. Such a simple problem, and I went on and on and on with it. That's it. Let me just do this. Well, at least we learned one thing, and that is what do you achieve when you give up? Exactly. You achieve nothing. And as frustrated as I was, because it's a simple problem, it's just I started it wrong, and when I know what I want to get, but I'm not getting there, right? So here is my change in radius in time is constant, and that's what what they wanted us to show. Let's see if we can solve something else. What else can we look at? Ooh, this is awesome problem. So over here we're going to have an airport. We're going to have one plane going towards the airport, right, that way, and another airplane coming in this way. Hopefully we will all agree that these two airplanes are separated with a distance d, and one thing we don't want is that distance to be 0. What happens when the distance is 0? Yeah, boom. So we have one airport and then we have two airplanes. Now, the good thing is that if you sit above those airplanes, you actually see those airplanes as moving on x and y axis or at some angle with the vector and so on. So for simplicity, so we don't have to chase the components of the vector I, j, and so on, we can just look at from the top view and let's say they're following x and y direction. So the airplane that goes due west is traveling on x-axis, and the one that is going due north, right, is traveling on the y-axis. So the distance over here that is to be covered is distance x, and distance over here that is to be covered is a distance y. Now these airplanes are also traveling at some speed. Now we know from before, I think 3.5 or 3.6, whatever it was, that we find the speed when we differentiate the path. Now the path is x, so the speed of this airplane is simply dx dy, and the speed of the other airplane is dx dt, and the speed of the other one is dy dt. So now, first off, what is the geometry of the problem? Triangle. So you start by realizing that you will be using triangle. Great. So you're using triangle. Now, we know a lot of formulas about triangle, right? We know perimeter of a triangle. We know area of the triangle. We know the area of the triangle. We know 6 trigonometric functions in a triangle. We know Pythagorean theorem also. So out of those 10 formulas that I listed, which is the one that we need to use that connects 3 things that we have? We have 2 lengths, x and a y, and we have the distance separation d, and we worry about that one because we know that we don't want that one to be 0. And we can observe at which speed that particular distance is decreasing between the 2 planes. Because it's clear that these 2 planes are going towards each other, right? They are not going head to head to each other. They are going in space. So you don't have to meet, right, head to head. You can meet in space. So which formula would be used for something like this? Do we care about the area? No. Great. How about those 6 trig functions? Are there any angles for this triangle? No, right? So we eliminated all of them. What's left? Pythagorean theorem and circumference, right? Well, Pythagorean theorem is good because I can write x squared plus y squared equals big D squared. And if I differentiate this in time, I'm going to get my dx and dy dt, right? And I will also get dd dt. What is dd dt? What is this?
How much the distance is changing? Time?
Yes. This is how fast the distance between the two planes is changing. Because as you can see, the distance becomes less and less and less and less. Right? So we can measure the speed of these two planes approaching each other. Remember, they're not going head to head. So you can't just take their speeds and simply connect the two speeds and say, okay, right? They're doing this in space, right? So we have to use this formula. So now when you hit this with the derivative in time, what do you have? 2x dx dt. We took the derivative of x in respect to time. Plus 2y dy dt. And 2d dd dt. These 2's are going to drop everywhere. And look what you have. You have the distance, how far the airplane X is from the airport, and the speed at which that airplane is moving. You have the distance that the airplane Y is away from the airport at the speed at which that airplane is moving. You have a physical distance between the two planes at the time and how fast they are moving as they're getting closer to each other because they're going for the same airport. Now, your radar at the control center is providing you with the information X and Y because that's the distance that we have, right? Satellite knows where the airplane is. Satellite knows where the airport is, the distance between them. So X and Y is something that we read off of the instrument. Pilots, or the computer of the plane, reports the speed. So we have all of these at all times. This one we can calculate here because we have X and a Y. So we also have D as a square root of X squared plus Y squared, which is what we already have. So we have 5 out of 6, and we are able to calculate how fast these airplanes are approaching. Would something like this be important as a calculation? And do we have a Joe sitting at a control tower computing this by hand? Where are your jobs? Let's take a look at something real quick. This is United States, and this is the current state of air traffic in United States, above United States. You think a Joe is sitting there computing where each plane is and figuring? This is what software does. Your job, if you're a software engineer, you have to code these formulas that we just did, and it's going to be multivariable because you have to track each plane. Going to JFK, going to LaGuardia, going to Newark Airport, you have the smaller airports around, and you have to follow the traffic. Right? Let's zoom in to Newark and New York area. Look at that mess. You can't even see the amount of airplanes here because they're on top of each other. There's many planes here. Now for each one of these airplanes, you get the entire flight, arrival, when they get... if you ever need to pick up anyone at Newark, you can just use this website, and when you see that the airplane landed, that's when you leave your house, because they still have to go pick up the bags and all of these kind of things. This is tracking them live, and if you actually pay money for this website, you can watch the flight from what's underneath the plane. You can see the ground. You can see the
How is this up?
Why? These planes are high up.
No,
So as you can see, it's a little bit busy. Oh, we finally loaded all of them. Much better. It takes time to load. And then that's Africa. And there's Europe. Look at that stream going towards China over there.
So there's only one plane in Libya.
Yeah. Maybe if you wait, it loads more. I don't know. There are 2, 3 almost. But look at that. So the problem we just did, right? The problem we just did is one of the crucial problems in developing the software that traces all of this. Otherwise, we would just have the planes crashing on every airport. Because, right? So we need to know the separation of the two planes, and then how fast that separation between planes is diminishing. You have the numbers, you plug the numbers, and you can calculate. And as I said, the distance, right? The distance x and distance y is what the control tower has from their from a satellite. And then dx dt, dy dt, the speeds of each individual plane reported by the plane or the pilot. And then capital D you can calculate, because you already have x and a y, you can calculate capital D, which is the separation at that moment. And then you have 5 out of 6 numbers. The 6th number is the one that you're looking for, which is how fast the distance between two planes is closing. You put this in the software, right? Run it, and we have safe airspace. Another problem is the problem of the one of my favorite design, so that you can record the rocket launch and not have Joe stand somewhere with a camera shaking, right? You design a machine that will have the camera mounted on the elbow, right? And then the servo is lifting the camera as the rocket goes up, and the rocket is always in the middle of the shot as you shoot the rocket up. So here's my device over here is the camera. It's a very sophisticated camera, as you can see. Put some buttons on it. There we go. And we have the very sophisticated rocket over here. with the fire. There we go. It's going to take off, and it's going to go vertically up with the height h, and clearly its speed, dh dt, because it covers height in time. So it's a vertical, right, vertical speed. So now my camera is going to shoot. This rocket is now too big for the way I drew the camera, because the camera is going to start shooting from here all the way up and needs to rotate this way with what we call angular velocity omega, but that is just a change of angle in time. This angle in time. And you have your length separation, how far the camera is from the rocket. You know that the rocket spews a little bit of fire when it starts, so you don't want to put camera and Joe close, right? So you have a place where you know, safe distance for the camera, and that's the distance L. And then we have the height, right, as the rocket goes up, and we have dh dt, which is the speed of the rocket. So you have to understand that this velocity, the angular velocity omega that you need to program into the controller, so controller turns the motor at a different speed, it's not constant. That speed is not constant, which is why you actually have to plug in the formula that the computer is going to calculate and turn the camera. When the rocket is close, is on the ground, just taking off, it's closest to the camera. That should be common sense, right? Because anytime when the rocket goes up, and rocket is here, the distance from the camera to the rocket now is bigger. So if the rocket is always going on a constant speed, it's accelerating, but let's say it's always going on a constant speed. If the rocket is going on a constant speed, the camera has to turn faster up in a first start of the trip than later, right? Imagine, well, airplane goes 500 miles per hour. And you just look at the sky and you can just look at the airplane flying for 10 minutes. It's really far away. It's going 500 miles an hour. Imagine having a car drive by you like 10 feet away at 500 miles per hour. For how long you're going to see that car, right? So, exactly. So, 500 miles per hour close to you and 500 miles per hour far away from you is not the same in your perception as a reference point. So, in this engineering design, clearly this camera needs to rotate fast in the beginning and then needs to slow down in its rotation to always have rocket in the middle of the shot. So now, all I need to do is to come up with mathematical formula that connects the values that I can read and transfers those into an angle. Then that angle in a controller is connected to how much the motor turns to spin the camera for the shot. So my first question is, what is the geometry of this problem? Triangle. And which formula do we get to use in this case for triangle? Are we going to use perimeter? Are we going to use area, trig, Pythagorean theorem? Exactly. There is an angle. All we care about is a change in angle. So, trig. Now, which trig function is going to connect all of these that I need? Sine has a hypotenuse. My hypotenuse is empty. Tangent. Tangent theta is equal to the height divided by the length L. Now, length L is constant number. 500 feet, 300 feet, whatever the safe distance is, I don't know, right? So L is going to be constant. Height is a variable which changes. So this is the variable. That one changes. And this one is constant. This one stands still because it is just a value. So now I can remember what I need. I need d theta dt, right? D theta dt. So d theta dt, I need to differentiate this in time. Now, we are not using quotient rule here because L is a constant. So it's just like 1 over L, you copy that. Derivative of tangent is, very good, times dt d theta, because d theta dt, because we took the derivative of theta in respect to time, equals to 1 over L times derivative of h is 1, and then we have dh dt. This is L. So I need d theta dt alone, because that's what I'm programming in. And on the other side, secant becomes a cosine, so cosine squared theta. Cosine squared theta divided by L times dh dt. The only thing that we are not happy with is the theta over here. dh dt is the speed of the rocket, so we have that. And L is how far we put the camera. Well, stretch the Home Depot tape, right, and measure it. 300-500 feet. So we have this. The only thing that I need to fix is theta. I am not allowed to have theta in this formula because we don't get to measure that anywhere. Now, luckily, we can read what cosine is on this triangle. And the cosine will, unfortunately, will involve hypotenuse. So I need to get that this hypotenuse here is the square root of L squared plus the height squared. So now, d theta dt is going to be square root of L squared plus height squared divided by L dh dt. And this is the formula that you would program into it. You know what L is, you know what the height is, you know how fast the rocket is moving. Actually, if you ever watch the SpaceX launch, they always put the speed of the rocket and height of the rocket in the upper right corner. That is that's just standard stuff they always do. Let's real quick take a look at the, let's say, Falcon 9 launch, or it doesn't matter which one. So here, there you go. So if you take a look at those two dials on the right hand side, top, stage 1 telemetry, you have the speed. It's going to go 1,000 kilometers per hour. When this gets to 1,600, it's going 1,000 miles per hour. And you think you're going fast when you're doing 80? Give it a few more seconds, and this rocket is going to be going 1,000 miles per hour. And now, so at this point it was going 1,000 miles per hour. Now look, Joe is not holding the camera really well, right? It's all a little bit shaky, which is why we want to, as engineers, we want to create something like this, right? And you go and you sell it to Elon Musk and say, okay, your launch is going to be much better if you use my device over here, right? That's where you make money. So as you can see, we always have the speed and we always have the height, the altitude of the rocket. So that's my DH/dt and my age, and then I know L, how far I planted the camera. So when you go and look into our equation over here, all of the quantities are known, and you will be getting, right? So now what you do is on the computer that it's controlling the controller that controls the motor, these values here in the programming are read off of the rocket immediately from the telemetry feed. So it adjusts quickly, and the computer is perfectly adjusting the motor to follow the rocket. And that's it. That's related rates. I love that particular problem because it's really, right, you get to really see these things at work. Now, in the past, my students from math club, they went to chemistry lab, they took some dry ice, cut in a little square, and then left it to melt in a warm environment and captured all of the water that was going, and they were measuring the time, and then the experiment matched experimental data to the calculation data. And when you overlay those graphs and you get one graph to be like this and the other graph to be almost the same as that one, oh, that's a lot of joy, right? Because you get to see, why mathematics drives everything on the planet, right? That's one of the great things. So if you want to try that, you certainly can. Another engineering thing, and this problem is not a joke, would be engineering a shut-off for a conveyor belt. A lot of businesses and things have to store stuff. So if you are at mines or quarries or farms, you put corn on a pile, you put gravel on a pile, you put coal on a pile. Anytime when you have something like that, like the sand, it creates conical piles. So if you have a conveyor belt coming in, right, and you have stuff on it, it falls off of there, and it creates a little conical pile on the ground. As the time passes, the conical pile becomes bigger. If this conical pile reaches the conveyor belt, the stuff will start accumulating on top of the conveyor belt and eventually break it off due to weight. And generally those setups are extremely expensive. So you get to design a shut-off switch, right? Now someone says, yeah, just put the photocell and don't worry about it, because when it reaches up, the photocell will be interrupted, the signal, and then just, but no, because generally these places have so much dust that any of the photocells would never be working. They need clean conditions. They would have lens, and their lens will always have dust on it, so it will always be closed, right? Or a bird flies by and closes your circuit or something, right? So that would not be good design. Can we figure out something that would involve time? And then you say, aha, well, related rates, because the change in height is the one that I'm worrying about, because the height is the issue here. And also, I'm connecting that to a volume, because that's what's coming in. The amount of stuff that comes up on a... Imagine if I am sending corn down this conveyor belt, and I have 10 people rip opening those bags, and 10 people at the same time pouring those 40-pound bags of corn, right? Scenario number one. Scenario number two, there's Joe placing one by one. Not the bag, I mean one little, what is it called? One little piece. Kernel, yes, thank you. One kernel at a time. So are the 10 guys with opening 10 bags going to send more corn volume? Or Joe placing one by one, right? So what's coming in is dV dt. That's what's coming in. Over here on the ground, I have my radius, which leads into dr dt, and I have my height, h, which leads into dh dt. So, as more corn or sand or whatever you have there is coming in, the radius is changing, the height is changing, and we have the change in radius and the change in height. Now, volume of the cone. What is volume of the cone? Volume of the cone is 1/3 pi r squared times the height. Do you need to know this? Well, the answer is yes, because they are extremely easy to know, and I will draw the chart of all volume formulas. There are only 3 that you need to know, and everything comes out of there. So we'll see that. Now, the issue here, and here I'll write it in blood, both of these are variables. So what happens if you are taking a derivative of 2 variables that are multiplied? What do you have to use? You have to use product rule. So, the derivative in time of this volume formula, I'm going to put pi over 3 r squared h, is going to be dV dt on the left, copy pi over 3, and now we have the product rule. Copy the first, derivative of the second, copy the second, derivative of the first. Note that I have dH dt and dr dt anytime I took the derivative, because none of those variables were time, so I have to follow with the chain. And now, this is what we have. This is the related rates formula, and certain things you can measure and plug into the equation. Now, sure, you should be able to spot the product rule. I said this problem is much trickier and harder than what we did so far. And the reason is when you're dealing with a cone, you have these three variables: volume, radius, and height, and they're all changing, right? But you don't have information for them all the time, all of them. So you have to, do some mathematical witchcraft to figure out whatever you're missing. And that comes from similar triangles, which is what makes this problem tricky. If you take a look at your cone as a cross section, your cone has this situation at certain times, right? When it's a smaller pile, it looks like that. When it's a bigger pile, it looks like that, right? So when you draw these triangles, you see that you have radius 1 and then radius 2, and the height 1 and the height 2. So we can write the proportion. What height 1 is to height 2 is the radius 1 to radius 2. And from here we can solve for any one of these. And then we get to differentiate this as well. We get to differentiate this as well to eliminate either one of these two in terms of the other. So there are, so I just want to work out the full problem for this with numbers, because usually I think your labs have it and homework will have it. So let's take a look if we can find the cone. Draining a conical tank. Problem 36. An inverted conical water tank with a height of 12 feet and a radius of 6 feet is draining the water on the bottom with the outflow of 2 feet cubed per second. What is the rate of change of water depth? What is the rate of change of water depth? So that's dH dt. When the height is 3 feet. So we only have 3 feet of water. It's about a quarter of 12, so let's put it over here somewhere. So this is how much water is left. Right? This height over here is equal to 3. Okay. Well, this number here is dV dt because it's change of volume in time. Volume is 1/3 pi r squared h. So we said that the dV dt is going to be pi over 3. Copy the first one. dH dt is the derivative of the second, plus copy h. And then we have 2r dr dt. I am not sure why I put this. Can you go back and fix this? You need to fix this, and you need to fix this. I have the formula right up there, but when I copied the formula, I put a 3. I could put a cube instead of a square, and I got the wrong formula. So please go fix that. All right, so now what do I have? This is where my R and my H are within the water that still needs to be drained. So if I look at this, they are asking me for dH dt, so I call that like I know it. dV dt is, I know that. I don't know, I know the height is 3. I don't know R, and I know the dr dt. So see, these are not known to me, so I have to actually work on this formula, and this is where the hard part kicks in, right? So we use the similar triangles. In this case, it looks like this. So this is my small height 3, and this is my big height 12, and this is the big 6, and this is the small r. So we can calculate value for r, but that's great. We'll do that. But before I do that, I need to write a proportion and take derivatives to connect dH dt and dr dt. So what big height is to small height, that's the big radius to the small radius. When you cross multiply this, you get 12r is equal to 6h. And when you divide by 12 to get r, you get that r is half h. So r is half h. And now we can differentiate that one to get dr dt. See, that's the one we don't need. That it's 1/2 dH dt, and that's the one we do need. So now we can plug everything in, and we have that the dV dt is equal to pi over 3, and in parentheses we have, instead of r, I have 1/2 h, so that's a 1/4 h squared dH dt, plus 2 times r, which is 1/2 h, times another h, and dr dt is 1/2 dH dt. So now these cancel. dV dt is equal to pi over 3. And now look what you have. You have a 1/4 h squared and another 1/4 h, and a half h squared, sorry. Half h squared. So that's 3/4 h squared dH dt. So it condenses really nicely into one equation. So maybe I should, let me just go and say this and this combines as 1/4 plus 1/2 equals 3/4 of h squared and then dH dt. So now 3 and 3 will drop, and the final equation that we get to use is pi h squared dH dt. And I have that this is 2 pi h is 3 squared dH dt. Now we're going to use a -2 because we are losing the volume of water. Yes? What happened? Oh, I dropped the 4. Yes, thank you. Yes. Pi over 4. I canceled the 3. There is a pi over 4 and then h squared. Yes, great. Thank you. So now this is negative 8 over 9 dH dt. So dH dt is negative 8 over 9 feet per second. So this is the height that you are losing. Remember, this conical tank is draining water down, so you are losing the height. You had the water level at a height, and then it starts dropping. I'm going to sketch out one problem and then show you the trick with volume, and we're done. Actually, I'm going to do the volume first, and then we sketch out the problem. Learn this, guys. Learn this. It will serve you well down the line in your engineering, especially mechanical and electrical and stuff like that. We have 3 groups of objects that we worry about for volume. The first group would contain a cylinder and a box or a cube, stuff like that. All of the volume formulas are area of the base times the height. So this is your height, this is your height, and this is area of the base. So what is the volume for cylinder? Well, base is a circle, so pi r squared times the height. What is the area of the square? Well, area of the cube. The base is a square, so a times a, or x times x. And then the height happened to be, which is h, is also x or a, so a cubed or a, right? So anything, or if you have a box, right? So it's not just, cube is a special rectangle, right? I mean, rectangular prism. This also has a height. So all of these objects that are like this, the second group I call spiky. That's where your cone goes and your pyramids. So if you have a cone or you have a pyramid, the volume is 1/3 base times height. So if you know the area equation for the base, then it just falls into one of these categories. So I don't memorize formula by formula. I know this list. The third group is a single object sphere or a ball. It sits here alone with a volume of 4/3 pi r cubed. Now your Calculus 2 will help you with deriving that formula, or Calc 3. This is it for all volumes across all of the shapes that you encounter. If you can figure out the area of the base, what is it? Is it a square? Is it a rectangle? Is it a triangle? Is it a circle? That goes there. Times the height of the object. Each one has a height. That's done. And now you're asking yourself, is it spiky? Yes, it is. 1/3. No, it's not. No, 1/3. Very simple. So 1, 2, 3 formulas cover all of the shapes instantly. So the question is just, can you find, do you know, right? Can you find what is the so look for that one. And the last question here would be to use the cylinder, because we did the cone, and you saw that the cone was not a joke. Especially we had those similar triangles, has a lot of variables. Now what we're going to do is we're going to take a cylinder, and this happens to be one of your, drinks. You put in a straw, and you drink. You have liquid inside. And every time you take a sip, the liquid goes down. So, next time you're out with a friend and drinking with a straw from a can, you can propose the problem and do some related rates. Maybe if you go out tonight already. Now, if you're going to drink a Cosmo from the glass, that's not going to be right. When I do this, that's inverted cone, right? That's much more work. It's for more impressive, obviously, right? The can, not so much work. So what do we have? We have a non-spiky object whose volume is what? Area of the base times the height. See, radius is not a variable. And that's what makes this problem easy. The liquid that you are drinking out of the can, let's say Sprite, will only be losing height. It will not be losing on the radius, where for the cone, it loses on radius. So now I have the derivative of the volume formula, and I don't have to worry about R because R is constant. I get to copy it. This is something that, if you don't pay attention in class and you don't pay attention on the video, the difference between the problems, because in one problem, R is a variable, on the other problem, R is constant, and that depends on what situation you have in the physical realm. So V dV dt is equal to pi r squared dH dt. So what you can bet your friend and make some money is that you can calculate at which rate the Sprite in a can is going down. You know the radius of the can. That's something that you can measure. The only thing that you don't know yet is dV dt. What is dV dt for this problem?
How fast you're drinking.
How fast you're drinking. That would be a sip. Have you ever Googled that? Do you think that that would be something that it's standard for human race? The size of a sip? It turns out it is. Yeah. So that's a number that you can Google. So you ask dV dt, you ask Google what is the average sip size, and it's going to give you a number. And then you know what the width of the can is. You can Google that as well for a standard can. And you have dV dt and you have r squared, and you can calculate dH dt. And your friend is going to be impressed. See what $600 does, right? She should go around brag that she can calculate things that no one cares about. It's amazing, right? So that's that. Now, if you watch my older streams for Calc1, like the previous semester or something, because I rotate problems, there will be, some of them you're going to run into a problem with a snowball, like in a cartoon, on the top of the hill. You put a little snowball and you push it, and as it rolls down, it becomes bigger and bigger. That's your sphere gaining a volume. So I draw this hill, and then I draw a little house and a person on the bottom. and then a person on top, and I label it as you because you are all terrible beings. That's given. If you're breeding, you're a terrible person. That's given. Or you think you're nice, but yeah. So you push this ball, right, and it goes bigger and bigger and bigger until it becomes bigger in the house and just flattens everything. We can calculate that, so that's one problem. The other problem that I do, if I don't do the airplane problem with the rates of 2 airplanes approaching, right, I do a ladder problem. Because if you want to clean a gutter, right, and your house is somewhat 90 degrees, right, to the surface, and you put the ladder up, you have the same triangle, right, the Pythagorean theorem. So the premise of the problem is that whoever is cleaning the gutter up there, right, is at that point on top of the triangle, and the bottom of the ladder is, so ladder creates hypotenuse. So there is the distance between the ladder and the house, x. There is the height of the house to the gutter, that's y. And it's the same with the airplane's head, right? Now, here comes you, terrible you. The bottom of the ladder, right? You kick it. So what happens when you kick the bottom of the ladder? The top of the ladder goes down, right? So now, how hard you kick the ladder out, that's going to be dx dt. And how fast the person is going to fly down, because there's no more ladder underneath, is dy dt. So you can calculate how hard is the person going to hit the ground. And I just present it as dy dt, and I just hope they have house insurance, right? Otherwise, it's yours health insurance is going to cover if you're doing the experiment. So it's the same problem as the airplane problem, it's just a different setting. You're still playing with velocities, vertical, horizontal, dx dt and dy dt, and the separation of, right, the two. And they do have a question like that, question 41. It's so funny with these titles. 41 says, ladder against the wall, and then the problem follows. Question 42, ladder against the wall again. Because the first time we didn't get it right? It's like we'll have another one. It's funny. And write down in your notes to take note of the problem 38, because you're going to do the project, right? Yes. So take a look at 38 in your notes. That's it. Bye.